Okay, so now we want to show that when we slide a test function left or right by a small amount, we take this guy and we slide it a little bit, that it doesn't move it up and down that much, that it doesn't end up with values that are significantly different in terms of any particular x. Okay, well, it's not that hard to see that this really isn't true for arbitrary functions. And so a good example is what I talk about in 2. Suppose you look at a function, the Heaviside function, the unit step function. Okay, we're defining with a closed dot here to be 0 here. It's not super important, although it just changes the details of how you do a proof like this. If you slide that left or right, let me use a different color. Let's slide it a little bit to the right. Well, then there is a substantial region here where they're not epsilon close, definitely. Okay, and if you didn't slide it very much, that region isn't wide. It isn't a wide region, okay, but who cares? The definition of uniform convergence is that you can give me any epsilon you want, no matter how small, and we look at this little band around the target function, the blue. Is that coming out? Yeah, I think so. And the red has to be always within the band for every t. That's the uniformity. And there's always going to be some, as long as I've shifted it at all, there's always going to be some little band here, or some little segment where I'm not in that band, the epsilon band. And so that's the geometry or the pictorial proof that this is not going to work. Okay, and it seems to have something to do with the discontinuity here, that the values jump so suddenly that if you then just then push it off to the side, you're going to open up this gap here where the values are not matching within epsilon. Okay, so well, I don't want to erase that. So just to make that really precise, just let's say epsilon. Let's say this jumps by 1. It looks like that as long as epsilon is basically less than 1, you're going to get a problem. So let's say let epsilon equal 1/2. You want to show a discontinuity statement, you often actually can pick a very specific epsilon. It has to be something greater than 0, but depending on the situation, you might be able to pick something very specific, like in this case. Okay, then let's see. Um, it's going to be easier. I think what I ended up doing was maybe, let me redraw it. I did, just to get it the cleanest statement. I think what I ended up doing was I shifted it left. Yeah, I think I shifted it left because just to focus on, to be able to focus on t equals 0 actually was helpful. And so if I shift it left, it's going to be like this. Okay, and so let's let t be some negative number. And we want to think of that as very small. We're trying to let t go to 0. And so this is very small. But the point is that no matter how small t is, we're not going to be able to make this within the epsilon band. Okay? And then what we're going to do is we're going to take the slid over function, and we're just going to evaluate that at 0. That's the red right here. That is not 0, and it's not even close, and it's never going to be close. Compared that to h unshifted at 0. Okay, that's the ordinary h function at minus t, just by the way the shifting works, minus, well, h of 0, I'll just write h of 0 again. Okay, and that's going to be 1. H of minus t is now positive. H of a strictly positive number is 1. That's still 0. That's equal to 1. And that's greater than our 1/2. And that's our epsilon. It's really a pictorial. The pictorial proof really captures it all. That no matter how much I slid this to the left, I'm going to get various points. I could have used all these points in here, but it was just convenient to just use 0 and say, okay, I'm not within, here's the epsilon band that I actually was going to use, 1/2, and then the epsilon band continues up here, but I'm just not going to be in that epsilon band. Okay. So that shows that when you have a discontinuity, and I slide a discontinuity left or right, then suddenly that's as if I made a huge jump. Even if the slide left or right is small, it's as if I made a huge jump in certain values of the function. And if I'm supposed to have all the values uniformly close, that's going to screw it up. Okay, so that leads us toward what we want to remember, test functions are super special. They're much more than continuous. So we're definitely going to be able to say we're going to salvage this in the case of test functions. But it shows us that we don't want to think that sliding left to right is never a problem. Okay, another one is that let's say we have g of tau equals tau squared. That is a very nice continuous function. Algebraic, it's smooth, it's all nice things, except one. Okay, let's see what happens when we move that left to right. Okay, when we move that, let's say to the left, these values are pretty close together in terms of the y values, but as this function gets steeper, a small change left or right ends up being a rather large change vertically. And that means that if I try to draw a uniform band near the blue parabola in terms of going up or down uniformly plus or minus in y, it's going to be quite a bit different from uniformly moved left or right. Okay, and it's all about the steepness. Okay, so the key here, we don't technically have to use the concept of a derivative here, but it really informs the proof and how we would do this, that g prime is 2 tau. Okay, and the fact that that's getting so steep as you go way far left or right, that means that a small horizontal change makes a big vertical change. Okay, so what we're going to do is, remember, t is going to go to 0. So we want to show that, here's what we want to show, sorry. It's in the handout. But as t go to 0, we want to show that this g translated, again, does not go to g itself, which is just g untranslated, g sub 0, uniformly. Okay. And let's see what we should do. So t is small. You want to think of that as a small number. And then we want to make the tau, the evaluation point where we're getting this to screw up, big. Well, an easy way to take a small number and make it big is, for any particular t, which measures how much we've slid the function over, we're going to look at the point tau equals 1 over t, and I claim that that's a good place to look to see that this is not going to work. Okay, and let's see. Let's just look at it. Let's just do the calculation. Let's look at the difference between the translated version, but by a small amount t, at this big number 1 over t, and look at g of 1 over t untranslated. Okay, so that is 1 over t minus t quantity squared, this is all in absolute values, minus 1 over t quantity squared. Just putting in the definition of the function here. Okay. Tiny bit of algebra, you get minus 2 plus t squared. Okay. And if t is small, and the whole point was that this is supposed to work when t is small, and we're showing that it doesn't, then we can assume that that's less than 1, and so that's greater than 1. Okay, so let's just set that to be your epsilon. If my band is 1 unit wide, that's a very generous band. Usually, you had to actually, if I was going to prove that it's actually uniformly convergent, then I would have to be able to choose any small epsilon. Epsilon equals 1 is being very, very generous and slack about the error bound here. And yet, if I go far enough out to tau equals 1 over t, then a small motion, that small t motion left or right, is going to pop me out of a band of even a nice generous width. Okay, so it's a good example of an explicit counterexample in terms of epsilon and delta kind of stuff. We were clever about something. In this case, it was where we measured the function, because of the uniformity insists that we should be able to pick anything, even something that's in a particularly inopportune place. And then we compared it, and we noticed, oh, that doesn't get small. There's no way to guarantee that small. In fact, it tends to 2, not anything small. Okay, so one thing that's important though is, let me contrast this again. I have chosen not to make a huge digression into concepts of like uniform convergence, things like that. It is true in this particular example that gt goes to g uniformly, or not uniformly, but pointwise. Okay, and this is a good example of the subtle issue of where the quantifiers go. To be uniform, I had to be able to pick an epsilon and make a boundary, make this band that works for every TAW simultaneously. To violate that, that meant I could pick the TAW strategically and just show it violated a certain epsilon bound. Okay, but if I just fix TAW at the start and then see if G sub t of TAW, does this go to G of TAW? That's a very different question, because I'm letting the speed at which it converges vary based on TAW. I've fixed TAW, and I just want to say that these converge sort of separately, not uniformly. Well, again, G sub t of TAW, that's just t plus, no, sorry, TAW minus t squared. Okay, that's TAW squared minus 2t TAW plus t squared. Okay, if TAW is a fixed real number, and t is going to 0, does this go to TAW squared? Absolutely. Okay, absolutely. If you analyze carefully how that convergence goes, the fact that I've got this TAW here means that it's going to be a little bit more reluctant to go to 0 when TAW is a really huge number. I'm going to have to make t much smaller if TAW is bigger to get it within a certain error bound of TAW squared. And that's what killed the uniform convergence. And in fact, that 2t is really just the derivative again. It's the slope. Okay, so this is pointwise convergence but not uniform. It's a really good example of pointwise but not uniform convergence. And so if we hadn't really elucidated that distinction, we might be confused. Be like, what could go wrong with TAW squared? And I did a little algebra and it seemed to work, but it does not work uniformly. Okay, so let's see. Alrighty, so now let me can this video right here, actually. This is a good place to stop. And then we'll finish up this thread of ideas by looking and seeing what exactly is it about a test function that avoids those two problems. And that's going to be introduce another concept, which is uniform continuity.